Section 13.3, Rational Exponents. The objectives: evaluate nth roots, translate between radical expressions and expressions with rational exponents, use the properties of rational exponents to simplify expressions. Nth roots. This table explains the different types of nth roots. Our first type is square roots. If b equals the square root of a, then b is equal to a to the 1/2. If 3 is equal to the square root of 9, then 3 is equal to 9 to the 1/2. Cube roots. If b is equal to the cube root of a, then b is equal to a to the 1/3. If 5 is equal to the cube root of 125, then 5 is equal to 125 to the 1/3. Fourth roots. If b equals the fourth root of a, then b equals a to the 1/4. If 2 equals the fourth root of 16, then 2 equals 16 to the 1/4. So nth roots. If b equals the nth root of a, then b is equal to a to the 1/n. Radical notation. If n is an integer greater than 1, then the nth root of a is equal to a to the 1/n, assuming the nth root of a is a real number. The expression nth root of a is called a radical. The symbol, the nth root, is called a radical sign. N is the index. A is the radicand. If no index is given, it is understood to be 2. For example, when we have just the square root of 3, it can be written with, we drop that 2 that's there, which will be the second root of 3, equals 3 to the 1/2. Something to remember about your index n. For the expression nth root of a, or a to the 1/n, to be a real number, we have to assume n is an integer greater than 1, which basically means a positive number. When a is non-negative, n can be any index. If a is negative, n must be odd. If a is negative and n is even, then the nth root of a is not a real number. Example 1a, 49 to the 1/2 is the square root of 49, which is 7, because 7 squared is 49. Example 1b, 81 to the 1/4 is equal to the fourth root of 81, which is equal to 3, because 3 to the 4th power equals 81. Example 1c, -8, that quantity, to the 1/3 power, is equal to the cube root of -8, which is equal to -2, because when I take -2, that quantity, to the 3rd power, it equals -8. 1d, 0.00001 to the 1/5 is equal to the 5th root of 0.00001, which is equal to 0.1, because 0.1 to the 5th power is 0.00001. 1e, -16, that quantity, to the 1/2 power, is equal to the square root of -16, which is not a real number. Any even root of a negative number is not a real number. Some of the rules for exponents. For non-zero real numbers a and b, and rational numbers m and n, our first rule, the exponent 1, a to the 1st power is a, as long as a is any real number. 2, when the exponent is 0, a to the 0 power is 1, as long as a is not equal to 0. Essentially, anything to the 0 power other than 0 is 1. our product rule, number 3, a to the m times a to the n is equal to a to the m plus n. When my bases are the same, I add my exponents. 4 is the quotient rule. A to the m over a to the n is equal to a to the m minus n. When I'm dividing quantities with the same base, I subtract my exponents. The 5th property is negative exponents. If I have a to the negative n, that is equal to 1 over a to the n. Also, if I have 1 over a to the negative n, that equals a to the n. Think about negative exponents just changing the position. If you have a negative exponent in your numerator, you need to move it to your denominator and make it positive. That's what's happened right here. If you have a negative exponent in your denominator, you need to move it to your numerator and make it positive. The 6th property is the power rule. If I have a to the m to the n, that's equal a to the mn. In other words, I multiply my exponents. Property 7, the power of a product. If I have the quantity ab to the n power, that is equal to a to the n times b to the n. You just distribute that exponent inside. Property 8, the power of a quotient. If I have the quantity a over b to the nth power, that equals a to the n over b to the n. Once again, you're just bringing that exponent in. If n is an integer greater than 1, m is any integer, and a to the 1 over n is a real number, then a to the m over n is equal to the quantity a to the 1 over n to the m, which is also equal to a to the m, that quantity, to the 1 over n power. In radical notation, a to the m over n is equal to the nth root of a taken to the m power, which is equal to the nth root of a to the m. Example 2, assume that each variable represents a positive real number. Each expression is changed to an equivalent expression in either radical or exponential notation. 2a, x to the 2/3 is equal to the cube root of x squared. The index 3 is the denominator in the rational exponent. This becomes your index. 2b, 3x to the 4/5. Notice that 4/5 is only on the x. This is equal to 3 times the 5th root of x to the 4th. That coefficient 3 is not affected by the exponent. 2c, negative a to the 3/2. Once again, the a to the 3/2 is separate from that negative. It's not in parentheses. That's equal to negative square root of a cubed. Negative 1 here is understood to be the coefficient. Example 2d. We have the 6th root of a to the 5th. This time we're going to change this into exponential notation. That's equal to a to the 5th sixths. The index 6 is the denominator of the rational exponent. 2e, 5 square root x, is equal 5x to the 1/2 power. In a square root, the index is understood to be 2. 2f, negative cube root of 4, is equal to negative 4 to the 1/3 power. The coefficient negative 1 is not affected by the exponent. We could also write it as negative 4 to the 1/3, which would be negative 1 times 4 to the 1/3. it's important. For the remainder of this chapter, we're going to assume that all variables represent positive real numbers unless otherwise stated. Example 3. Simplify each expression using one or more of the rules for exponents. A is x to the 2/3 times x to the 1/6. Our first steps to add the exponents, since we are multiplying the same base. We have x to the 2/3 plus 1/6. Getting a common denominator, that's x to the 4/6 plus 1/6, which is x to the 5/6. Example 3b, which is x to the 3/4 over x to the 1/3. Here we're going to start by subtracting our exponents. So we have x to the 3/4 minus 1/3. Getting a common denominator, that gives us x to the 9/12 minus 4/12, which is x to the 5/12. Example 3c, we have the quantity 2a to the 1/4, all to the 3rd power. We're bringing that 3 inside, which is going to equal 2 to the 3rd times a to the 1/4 times 3, which is going to give me 8, but that's what 2 to the 3rd is. And then 1/4 times 3 is 3/4, so we have 8a to the 3/4 power. 3d, the quantity 27y to the negative 9/10, all to the negative 1/3 power. We're going to, again, bring in that negative 1/3, which is going to become 27 to the negative 1/3 times y to the negative 9/10 times negative 1/3. We're going to multiply the exponents of y and reduce. In this step, we have moved the 27 to the 1/3 power to the denominator because it was negative here. We moved it down here to make it positive. Y to the 3/10 is staying up top, and that's what happens when I multiplied negative 9/10 times negative 1/3. So now I'm simplifying, and my final answer is y to the 3/10 over 3, because 27 to the 1/3 power is 3. 3e, we have the quantity negative 36 to the negative 1/2 power, which gives us 1 over negative 36 to the 1/2 power. That is not a real number, because negative 36 to the 1/2 power is the square root of negative 36, and we can't take the square root of negative numbers and end up with a real number. Example 3f, we have 9 to the 2/4 power, which is 9 to the 1/2 power, which is simply 3. The exponent can be reduced as long as the expression is real. Example 3g, we have the quantity 49x to the 6th, y to the negative 2, over z to the negative 4, all to the 1/2 power. That is, now we're separating it into a numerator and denominator. We're going to have the quantity 49x to the 6th, y to the negative 2 to the 1/2 power, over the quantity z to the negative 4 to the 1/2 power. Now we're going to bring that exponent inside. That's going to give us 49 to the 1/2 power, x to the 6 times 1/2, y to the negative 2 times 1/2, over z to the negative 4 times 1/2. 49 to the 1/2 is 7. 6 times 1/2 is 3, so we have 7x to the 3rd. Negative 2 times 1/2 is negative 1, so we have 7x to the 3rd, y to the negative 1 in our numerator. And then negative 4 times 1/2 is negative 2, so we have z to the negative 2 in our denominator. And now we'll start simplifying things. So the 7 is going to stay where it is. The x cubed is going to stay where it is. Z squared was in my denominator and negative, so I move it to my numerator and make it positive. Y to the negative 1 had been in my numerator and was negative, so I moved it to the denominator and made it positive. So my final answer is 7x cubed z squared over y. Example 4, simplify each expression by first changing it into an equivalent expression with rational exponents, then rewrite the answer in simplified radical form. 4a is the fourth root of the cube root of x. So the first thing we're going to do is eliminate this first radical here, and we're going to turn this into the cube root of x to the 1/4 power. And then we're going to take the cube root of x and use rational exponents for it. That's x to the 1/3 to the 1/4, which is x to the 1/12, which is the 12th root of x. We came up with that because 1/3 times 1/4 is 1/12. Remember, here we multiply our exponents together. Example 4b is the cube root of a times the square root of a, which is a to the 1/3 times a to the 1/2. When my bases are the same, I'm going to add my exponents. So this is going to become a to the 1/3 plus 1/2. Getting a common denominator, that's a to the 2/6 plus 3/6, which is a to the 5th sixth, which is the 6th root of a to the 5th. 4c, we have the square root of x cubed times the cube root of x squared all over the 5th root of x squared. This becomes x to the 3/2 times x to the 2/3 all over x to the 2/5. In my numerator, I'm going to add my exponents. That's going to give me x to the 3/2 plus 2/3 all over x to the 2/5. My common denominator is 6, so on the numerator I have x to the 9/6 plus 4/6 all over x to the 2/5, which is x to the 13/6 over x to the 2/5. And now I'm going to do the division, which is subtracting the exponents, so that's x to the 13/6 minus 2/5. Coming up with a common denominator, that's x to the 65th 30ths minus 12 30ths, which is x to the 53rd 30ths. Now that's x to the 30 30ths times x to the 23rd 30ths, which is x times x to the 23rd 30ths. And here we just wanted to make sure that we have 1 plus the fractional piece, which gives us x times the 30th root of x to the 23rd. This is significantly more complicated probably than any problem you'll encounter in your practice or your certify, so don't worry too much about that.